How statistically unlikely is that? We could discuss that, but anyway. All right, let's talk a little bit about. So last time, what did we talk about? Histograms. And then what do we do with the histogram? We came up with the concept of a probability distribution function, which is like a histogram in the limit of many observations. And then what else did we started quantifying those to talk about the shape of that distribution a little. So what were some of the quantities that we talked about?
The variance,
mean, skewness, and basically all those moments, and then the centralized moments. So remember, we were thinking about things that were like expectation values of the value, expectation values of the value squared, or maybe expectation values of the value minus its expectation value squared. So this is the normal way that you talk about the variance. This is the second moment. This is related to this, because we did a little algebra to show that this was actually equal to this. Right, so, and then the skewness was the next one up, x minus. So, we can make all of these, and how do we get one of these? Like, what is this little angle bracket meant? What kind of way to get it?
Summation.
We could do it either as if it was a discrete one, we could sum over all the probabilities of that value times that value, 1 to the number of given. Right? Or we also said if it was continuous, we could have written it as an integral x dx over, whatever, the minimum, the maximum, whatever the whole range was that you could possibly have. And if it was the second one, it's the same thing, except we would just raise this, actually let's write it like this, put it to the nth power. Right? And so subtracting off the mean before we raise it to the power and whatever centralizes it. So it's kind of like, we're not going to talk about we're not going to talk about parametric distributions yet, but here's a bell curve, say. So this is x, and this is the probability. So here's the mean of x, the expectation value of x, and the spread of it has something to do with x squared minus x squared, like that, right? That's something about the width. And we'll get more careful about that in a little bit. But, like, since this isn't at 0, what this does essentially is it centers it on 0 before it takes the square. Whatever, is that right? X minus x. X minus x squared average. Right, so this subtracts off the average and makes it, we're measuring things relative to the center. So that's the idea. And then the skewness, this one is the same. This is the skewness. This is the variance. And, like, actually I've drawn a nicely skewed one. So this one has is lopsided a little. So this one has a little bit higher than that one. So this one would have a negative skewness because it looks like it's a little higher here than it is for the equivalent side there. So it's a little bit more likely to be like it's kind of tilted over a little. Does everybody see that? Okay. So that's a big part of the game. But one of the things that we closed on last time was we would like to talk about in our histogram world, you're either in one bin or a different bin. You're not in two bins. So we'd like to think about things that are not mutually exclusive. So knowing that you are in one Venn means you're definitely not in another Venn. But like, we'd like to think about things that maybe we have a probability of being in both categories, because we would like to think about other classifications of like exclusion and inclusion into different sets. So the way that people normally do that is with a Venn diagram. And so we're going to talk a little bit about Venn diagrams and thinking about probabilities like that. All right, so we are. Okay, so I don't know. All right, this is like the nerdiest thing ever. I spent a lot of time while doing this. I also just think this is fun to go online and look at people's funny Venn diagrams to see what like they have come up with, because frequently you can think of that. But so everybody remembers how to do it. Like maybe you have something like this, and then even though you could imagine that this is just a part of the whole world, let's put that on top. So this rectangle tells us the whole possibility of everything. Inside one of these is like condition A, say, condition B, and then this is not A and not B out here. So if area, I mean, we could grid this with little points if we wanted and make it a discrete set, or we could just think of it as like the area of the space is the representative of how large the probability is. So how do I calculate the probability of A?
The area of A over the whole.
Yeah, so the area of A versus the area of not A. So we could, and if this is the whole world, then the probability of the outside is 1. So we can think of the probability density function of A and integrate it, or let's just say, let's do it this way. We sum over all the grid points. Let's grid it up, because I find it a little easier to think of it in terms of summing rather than when we're thinking about how to relate to the histogram. So count the number of points that fall in A, and then the number of points that don't fall in A, and that's where we are. Right? So the probability of A is the sum of the number of points where A is true, or inside A, divided by the total number. So I always do this, and then I don't know how many there are. Okay, let's pretend that there are 50 points. I think I actually made 60. No, I made 55. Okay, now it's 50 points. So, so in this case, whatever that is, maybe 16 or 20. So it's going to be something like 20 out of 50, or whatever it is. And what's the probability of B? Same thing, right? Except it's a different size. So let's say this one has, it's not going to be 30 out of 50. Let's say it's 17 out of 50. Okay, what about, so are A and B mutually exclusive? No. Okay. What would they look like if they were mutually exclusive?
They wouldn't touch.
They wouldn't touch, they look like this. So this is mutually exclusive. Okay, so then there is a common region, which is this area in between them. So in that area, you're both A and B are true, right? So, make sure I got all the notation, because I always get it wrong. So, probability of A B is the shared part. So probability of AB is the, and let's make it simple. This is the number in A over the number. This is the number in B over the number. This is the number in A and B over the number. Okay. There's another set which is interesting in here, which is not this one. How else might I combine A and B? So this is like A and B. A or B would be what? And interestingly, probably A or B is written this way for reasons which are clear only to. This is why I get it backwards every time. So this means the probability of being in either in A or in B or in both, it's all fine, okay? But how do I count that one up? Is it the number in A plus the number in B over the total number? Almost that. What's the problem with that? It double counts which part? The overlap. So I need to subtract off that one time because this is counted in there and it's counted in there, so I need to subtract off one of them to get that. Okay. So one fun game to play with this is like, so how many of you taken like a programming class? Yeah. Do you remember the and, the or, the exclusive or, and all those funny things? It's kind of nice to think about these that way, where it's like, I could be in A or B, or I could be in A or B, but not both. I could be, those kind of things are just ones. But when you draw the Venn diagram, it's pretty straightforward to imagine like the possibilities. Does that make sense to everybody? Frequently people just start off writing these things down and I find it completely insane and I can't, and then I confuse between this one and this one. I find it much easier to think about when I have this drawn. Okay. So now we would like to talk about like mutual exclusivity in terms of these quantities. Here's our mutually exclusive. How can I express the concept of mutual exclusivity in terms of those probabilities? Yes, this guy, the double one, the union one, PAB equals 0. That's one way of expressing it. What about this one? Can I say something about that guy if that's true? Yes, I can say that second statement. I can say that equals P of A plus P of B. So now we start to see why the notation makes a little sense. Does that make sense to everybody? This notation also makes sense because it turns out that when you multiply the probabilities together, you can do it in such a way that only when they're doubled up do you get something that's non-zero. Like you can squash it, but there's a similar kind of formula. But so what happened here is, right, we threw off the probability of AB, the last bit there, by saying that was 0. could have written this out as probability A plus probability B minus probability B. Right? Everybody's on board with this? Okay, why is this helpful? Like what kind of an experiment might I come up with that where this would be really important to check? Like I can do an experiment, right? Maybe I'm detecting A, got my A detection instrument, and I've got my B detection instrument. But suppose they like don't fit in the experimental apparatus together. So I can either choose to measure A or measure B, but I can't measure both of them. So I can't decide whether I'm in this region or not. How can I use this formula to figure out whether could I use an experimental design like that to figure out whether this, could I check this formula basically? I could. So suppose I said that, if I use my A thing and I come out and say, all right, that 20% of the time I'm doing this, and 30% of the time I'm finding this, but then when I take all of the collection overall, I actually find that this is 50% of the time, then I know that this guy actually had to be small. Does that make sense to everybody? So it's kind of like deductive work to figure out whether they're mutually exclusive or not. So this is the part of the game of how you use the probabilities is like you may not be measuring the thing you want. You might be measuring something else next to it and then using these kind of logic rules based on the Venn diagrams to build closer to the thing you want. This is sort of maybe one of the simpler ones. The one that people get really fired up about is one called Bayes' theorem, which we're going to work our way toward over the next few minutes. Okay? So, what's another thing that we might want to describe other than mutually exclusive? Which is kind of related to that concept. Like, if I'm mutually exclusive and I make a measurement, before I make the measurement, this is sort of like, okay, there's a funny thing in the world called, so I talk about this as being Plato versus Aristotle in the book, but it's like, there are groups of statisticians who think of the world in a Bayesian framework, and then there are groups of statisticians who think of the world in a frequentist framework, and they're like, kind of like Democrats and Republicans, they don't really, it's more about like the preconception of where they're coming from than it is about their particular stance on any one thing. But a Bayesian essentially believes this Venn diagram exists before you make an experiment. Like there is an underlying probability, like a Platonic solid, like Plato would have said, there's something, I know what a circle is. I may not ever have witnessed a true circle in the world, but there's like an idea of what a circle is. And the Aristotelians said, no, everything has to be in the real world. Those conceptual things are just an approximation of the real world. So which one is the one that's real? So Bayesians think there is an ideal like probability distribution that exists out there and not in the real world. Every experiment is not actually the probability distribution. It's just an estimate of it. But they think that there is actually an underlying probability that you should think about, which is the probability if I did an infinite number of experiments. And frequentists don't like that idea. They just say, how many experiments you do, let's describe them. So there's no abstract probability. It's just like, once you got your data sitting in front of you, manipulate it. So that's two different framings. It is a little easier I find it easier to think in the Bayesian framing because I like to draw a little figure first and then say, okay, now I'm going to go make measurements in this probability space and think about how it works. That sort of makes sense to everybody. Okay. Mutually exclusive. If I make a measurement and I could either measure A being true or B being true, and suppose I do the A measurement first and then the B measurement second. Does knowing whether I am A or not affects the outcome of knowing the second measurement, whether I'm B or not? So make measurement number 1, and I can either have A or not A. And then a little bit later I make measurement number 2, and I can either have B or not B. So careful. If I measure the first one, and I know I am A, and I have this probability space, then do I know what the answer of the second experiment is?
So you already see the probability space?
Let's assume that these things are mutually exclusive. So let's suppose we don't actually see this, but we're exploring this space. But we, as the posers of this interesting thought experiment, actually do know that this is the probability space. So you got 2 mutually exclusive things, A and B. So I'm making measurement number 1, and I find A or not A. Does that affect the probability of B or not B? It doesn't affect it in the abstract, but if I am measuring the same thing, like it could be an apple or an orange. I measure, is it an apple? And if my answer is no, does that affect my possibility of it being an orange? Yes. Right? So mutual exclusivity does not mean the same thing as statistical independence, which we're going to talk about in a second. So this is an easy thing to get confused. I have these 2 things. They both have separate probabilities. So I can talk about the probability B and I can talk about the probability A. But when I start thinking about the probability of their overlap, both A and B, or the probability of these, being mutually exclusive tells me something special about that space. It tells me that this is 0, but it also tells me, so if I know whether this one is true or not, does it affect this relationship? So in this case, I have probability of A plus B equals probability of A plus probability of B. But if I write down a separate thing, so the probability of B, given that I know that A is true, what's the probability of B when they're mutually exclusive? Zero when they're mutually exclusive. Right. Okay. Let's put this in the mutually exclusive one. But this one, both of these are in the mutually exclusive one. This is supposed to be the warm-up to doing the same thing in this case. Okay. So everybody see, yeah.
So if you were to find that it's not A, you're not saying that it would be B, correct?
Yes. The probability of not A. What's the probability of not A? Probability of B, given that it's not A. Let's write it out with numbers. So I take the first measurement, I don't know anything. I could either be inside the A or outside of the A, or inside the B or outside of the B. How many do I have total? Big N. Inside of here I have the N of A, inside of here I have the N of B. Out here I have N minus N of A minus N of B. So what's my probability of B if I know that A is false? This isn't the probability of B. Because the probability of B is NB over big N.
It's kind of B over N minus N of A.
Yes, it's N of B. We have reduced the space. Once we're outside of this one, now we're only outside of this one. So it's the probability of this guy minus this one plus this one. So it's N of B over N minus N of A. Okay? And so this is sort of like, these are all the games that you play if you're playing like poker where you don't reshuffle the deck. Because when you see a card, it changes what's left in the deck. Essentially, like if you put all the cards back in and reshuffle before, like every time you've got all the cards, they're all equally likely. But once you've seen one, it changes the likelihood. So if you see an ace and you know the ace is not in the deck anymore, then the odds of drawing the ace is less than it would have been, because there were 4, now there are only 3. So that's the kind of thing that these sort of logical probability constructions are going on. Okay, everybody on board with this? Okay. So what's it like in this one? What are my probabilities of A given B, and the probabilities of B given A, etc., sort of thing?
If it's given B, then the probability that it's A would be probability that it's AB out of B.
Yeah. Exactly. So, probability of B, probability of B given A is, okay, first we're given A, so we don't have the whole space anymore. Now we're in this space, so it's probability of AB, or the number of AB equals the number of A. Cool. Everybody's got that? And we could have done it the other way around. All right. But these are the numbers. Let's use these formulas to write it in terms of the probabilities. So what's a useful one over there? Probability of AB gives us the number of AB, right? So I could write this as n times the probability of AB. And I could write this as n times the probability of A. Everybody see that? And now, even though we were talking about this restricted domain, because the probabilities were defined with the whole domain in mind, it's the same n. So these cancel. Okay? And the same thing is true here. Okay? So, we can write a couple of nice little results out of this. The probability of AB is the probability. Right? I've done terrible notation the whole time. Yes, I know. In the notes, I've been writing these there rather than there. The little subscript one, I had them before the parentheses in the notes. It means the same thing. I'm just going to start writing them that way so I'm more consistent with the notes. Does everybody understand what I mean? applying this over to that side to get those two. Everybody see that? So the probability of the union is the probability of A given B times the probability of B. And this is why this notation, with this looking like a multiplication, is this, because this is a multiplication. Does everybody see that? It's not quite a pure multiplication, because there's this little dude lingering down here, which this isn't just the probability of A, this is the probability of A given B. This is the probability of B. Okay? So Bayes' theorem is exactly these. Probability of A, B equals probability of A, B divided by the probability of A. Okay. This is all just like algebra, right? Why is this one like so deep that there's like classes and classes and classes about just this object? So we want to try and learn how to think about this one a little bit. Okay. Suppose I'm thinking about an experiment, and suppose A is my data, so I've collected some observations. Now I want to make another observation that is based on my first set of observations. And I want to know whether that new data forces me to reconsider my theory. Okay? So I have a theory that I think explains all the data I've got. I'm going to go out and make a new experiment. So B is the outcome of the new experiment. A is the data I've already collected. But I don't have anybody as absolutely true. So what this tells me is when I'm making new experiments, given the results of an old experiment, how I update what my expectation is. So if I do something, and so it's a little bit like thinking about this space, like the first experiments tell me that I seem to be inside of A, and then the second experiment tells me that AB is the fraction of A that's available to me. So when I go to measure whether B or not is true, it depends on the fact that A is already true. So this is the one where they say, here's my example. So, do I have it in here? So this is one of those ones where like a person wears glasses. Is that person an engineer? What's the probability of that person being an engineer? Is that greater or less than the probability of being an engineer?
Greater.
This is what you want to say, isn't it? But it's exactly playing this game where it's like we have a notion that the kind of people who would be wearing glasses would be the kind. We're thinking about these conditional pieces, and Bayes' theorem is the way you put those pieces together and then think about it. So probability of A would be the probability of wearing glasses, probability of A would be the probability of wearing glasses and also being an engineer. And so you can get yourself into very funny logical traps if you don't think this way, because it's quite different to do that. Does that make sense to everybody? So, so the outcome of our new experiment depends on the outcome of our previous experiment in Bayes' theorem. And so when we go to test, when we go to test a new experiment, if we think about the probability, like we said here before, if we think about the probability of B and the probability of A independently, if we take the first experiment and it says A, and then we make the second experiment and it says B, that isn't possible. So they're actually linked together. Does that make sense to everybody? And Bayes' theorem is the thing that helps you sort that out, like how to put those probabilities together. The probability of the combination is not equal to the probability of B to start out with, and it's also not equal to the probability of A to start out with. Does that make sense to everybody? Hello? Yeah.
Do you have an example of, like, in an experiment, like what A or B could be?
Oh, yeah. So, let's think about this. So suppose we have there's a relationship between temperature and salinity. Let's make a, you probably know regret this, but I'm gonna, suppose I can go and I can measure the temperature, I can go and I can measure the salinity, but underlying in the real world, there's actually kind of a range of possible values. So if I was making all the measurements of temperature on their own, I would get like a histogram, a probability like, it looks kind of like this, along the temperature axis. So maybe these are the most likely and these are less likely. And if I went and measured just salinities, I'd have kind of a probability distribution like that. So measuring only salinities, let's say this is 10, this is 10, just to keep our lives easy. What's the most likely measurement of salinity? 10. And what's the most likely measurement of temperature? If I measure temperature first and find that it's 2, now what's the most likely measurement of salinity? Not 10. It's somewhere on this end of the distribution. Does that sort of help?
That assumes that they're directly proportional.
They don't have to be proportional, they just have to be related. So that's the nature of this concept, is like the fact that this zone is different. Yeah, there is a relationship. So knowing information about salinity gives me information about temperature. So even without measuring the temperature, I'm constrained once I know the salinity. So in this case, it would be, the probability of finding temperature 10 is not the same as the probability of finding temperature 2, but the probability of finding temperature 2 after I know that salinity is 2 might actually be quite high. Does that make sense? So the probability of finding a particular temperature, not knowing anything about salinity, is just that original distribution. But the probability of finding a particular temperature, knowing that my salinity is low, is affected by the probability of finding that salinity and the probability of them being together, which is like the area that combined figure fills. Does that sort of make sense? So let's think of the alternative and see if we can come up with that. What would happen if these were independent measurements? What if temperature and salinity were independent? What would the data points look like? It'd be uniform, or it could even be a ball, but it wouldn't have any direction to it. So let's imagine it's a ball. So now, I measure a temperature, I find out it's, oops, sorry, no, you're right, it does have to be a square. It's a square. I measure the temperature, and I find it in that range. Does knowing where I am on this axis affect the likelihood on this axis? Not at all, right? Like whatever this distribution is here, what I'm trying to illustrate, which I'm not doing a very good job of, is that any slice through this data set would have the same distribution of points. Any slice in this direction would have the same distribution of points. So in that case, the measurement of temperature and the measurement of salinity will be independent. Right? I am not, how do I write independent in this language? I would say that the probability of B given A is equal to what?
Still probability of B.
It's just the probability of B. Unaffected. Okay. Well, what does that tell me about this formula? If probability of A given B is equal to probability of B, that is equal to, under all circumstances, probability of A times A and B over the probability of A, which means, so independent. This is not the general case. This is our box of describing independence only. Probability of B given A is the probability of B, and then probability of B times the probability of A is equal to the probability of AB. So now we really see why the AB notation is powerful. Mutual exclusivity occurs when this funny one that has the plus inside actually equals the plus. If it looks like a linear operator, that means this one is 0, which means they are mutually exclusive. Everybody got that? This one looks like we've just distributed the p across the multiplication. Looks like this. You can't actually distribute the p across because we should have had to have weird little funny subscripts on either this guy or this guy to get a Bayes theorem form. This one tells you that the probability of AB is the product of those, but only if they are independent. So now let's talk about our eyeglasses case. So the probability of being an engineer and wearing eyeglasses, is that equal to the probability of wearing eyeglasses times the probability of being an engineer? Or do we think it's not? That's the question. Like, is there no relationship or is there a relationship? Does that make sense? So, why would we have to go out and collect some data to figure that out? And maybe we have intuition about what that would be. Nonetheless, this is actually something that we can use to test whether those are independent notions or not. If they are independent, then once you have collected the probability on eyeglass wearing and the probability on engineer, you could multiply them together and ask this question. Does it equal this? Bayes' theorem will work whether or not they are independent. That's the big difference between this one and this one. Does that make sense? So this one is true in general. This one is true only if those two data are independent. Okay. Last thing we're going to do. How do I draw independence on this figure? How would I draw A and B being independent on a Venn diagram? And it's going to be quantitative, we'll give you that hint. It's not just a shape. It's shape and area together. Is there no overlap if they're independent? Not necessarily. Like, in fact, there can't be unless one of them has 0 probability. So there has to be overlap. It has to be A, it has to be B. What does this tell us about the number of things in B, the number of things in A, and the number of things in AB? They have to be proportionally intersectional. So the number of things in A versus the total size has to have the same proportionality as the number of things in AB versus the number of things in A. So it's this kind of a game where we have number of things in B to the total number of things in A to the total number equals the number of things in A, B to the total number. That's what this one says. But I could then go and use this funny formula to break that up and figure out that basically the ratio of this inside this has to be the same as the ratio of B inside the whole. So the probability of B without knowing anything about A is NB over N. The probability of B, if I do know A, is AB over A. So NB over N equals NAB over N of A. Or, can we range it? N of A over N equals N of A B over N of B. That makes sense? So if A is 10% of the total area, then this versus this has to be 10% of this area. Or vice versa. If B is 20% of the total area, then AB has to be 20% inside of A for independence to be true.
Sorry, this might be a silly question. Can you just give it like why mutually exclusive and statistically independent are different things? Like what the definition?
Absolutely. No, it's not a dumb question at all. So mathematically, it's this versus this, that the probabilities, the product of the probabilities is the probability of A, B. And here, it's that the sum of the probabilities is the probability of both of them. That's the first, that's one equation form. But secondarily, look at the Venn diagrams. They can't be the same. The Venn diagram for mutually exclusive means there's no overlap. That's mutually exclusive. The Venn diagram for statistically independent means there must be an overlap. Because simultaneously, the number of things in B to the total number has to be equal to the number of things in this part versus the number in A. And the number of things in A versus the total number has to be the number in AB versus the number in B. So if the number of things in AB is 0, that is, if they're mutually exclusive, then the probability of A and B must be 0. No, either one or the other has to be 0. We're just going back to this. So mutually exclusive means this is 0, which means that one of those doesn't exist. Does that make sense? So they are not the same thing. You cannot be both mutually exclusive and statistically independent. Even though we frequently say them in words like they are interchangeable, they're in fact not. They're two separate concepts. Does that make sense? And these two Venn diagrams tell you. If you can grind on those a little bit more.
So if the probability of A is something, the probability of B is 0. I mean, just that automatically means they're mutually exclusive? Or
Yes, it does,
Okay.
because the mutually exclusive, if P of AB is 0, and P of AB by Bayes' theorem is equal to the probability of one of them, so if the probability of one of them is 0, then P of AB is also 0. Like once one of their probabilities has gone to 0, then they are mutually exclusive. But
can't you still prove that though? If like PB is 0, PA is something, it would still be equal to the probability of AB.
it would,
0.
it would still be 0. Yeah.
Okay. Okay.
So
But then isn't that just for
this is for independent. So
Yeah.
if you take independent and try to also make it mutually exclusive, that's where you're forced to make one of these 0.
Okay. So you can have Oh, this
Yeah.
time, okay.
So this is a little bit like which mythical creature doesn't cast a shadow. What's the answer to that? Or which mythical creature can't see itself in a mirror? Same thing. All of them. They don't exist in the first place. And the probability of them having anything be true about them is true. Right. Anyway, on that note, we're done. But this is hard to wrap your brain around. But the idea is that one set of observations informs another set of observations unless they're statistically independent. Most things in the world are not statistically independent. So when we go to talk about statistical independence, we're going to have to be really careful what we mean, because it's much easier to do lots of stuff when we say things are independent, but frequently enough.